Welcome. In this video I'll discuss field-aligned coordinates and field-aligned meshes, which are commonly used for linear and non-linear simulations and calculations in plasma physics. And first I'll discuss why we need, or why we often use field-aligned coordinates, so some of the problems with non-aligned coordinates and what attempts have been made to overcome them. Then I'll go through in approximate chronological order the different methods which have been developed and used. So there's the simple flux tube scheme, which is often used in for example, gyrostatic fluid flux tube codes. These are often called ballooning coordinates, which is a slight variation of them, depending on how they're closed in the poloidal direction. Then there's a variation attributed to Dimitz and Bruce Scott, I think separately, developed this method called shifted metric method, with slight variations on this. And then there's more recently, in the last few years, the FCI, or flux coordinate independent scheme. And these all have some advantages and some disadvantages, and I'll try and explain them. So first, the non-aligned coordinates. So one option is just to start with a grid, whatever grid you like really, and then solve the equations on it. So this could just be a simple Cartesian grid, like this. So we have a simple square grid. We have a set of partial differential equations, like MHD for example, and we can just solve them on a grid, and this is fairly straightforward. So we just have some kind of some simple grid spacing like this, some simple grid spacing in X. So we can write down finite difference formulae or finite volume, or in this kind of geometry it's quite straightforward to do things like spectral methods, so Fourier transforms. And these kind of things are used often in astrophysics simulations. And the reason is that if you have a case where you have high beta, so for example you have magnetic fields which are very complicated, so you might have there's like a B field here. You might have B fields changing. So you have a B field which is moving, so you have this is kind of moving in time and changing, for example. So if you have a changing magnetic field, so it's typically where there's high beta, so we have very large thermal pressures, and so the magnetic field is being pushed around by the plasma. This is often the case in, say, astrophysics and solar plasmas, whereas in laboratory plasmas like tokamaks, there's a very strong guide field which enforces a particular direction in general on the field. But in this case, where we have magnetic field lines in different directions and they're changing in time, it's very difficult to align a grid, align anything with the field lines. And so the simplest way is just to have a grid which doesn't align to the field, and then to try and solve it as accurately as you can. So you just grid up your methods. If you're in, say, a periodic domain, or a very large domain, you might be able to use high order schemes, so high accuracy schemes, and minimize the errors associated with this. But in general, there's a problem with things like transport. So particularly transport parallel and perpendicular to the magnetic field. So parallel, I'm just going to look at the notes like this. So this is parallel to the B field, and then this is perpendicular to B, and the parallel transport, this is much larger than the perpendicular transport. So because essentially particles are free to move along these field lines, whereas they are usually constrained by LAM orbits to move across the field lines. And so things like heat flux can be many orders of magnitude higher along the fields. So heat flux along the field, so say if we have a high temperature here, low temperature here, the heat flux along this field is very hard to model accurately when you have a grid like this. We could draw a simple picture, try and explain this. So we have a grid like this, and then we have a magnetic field which is, say, like that. So it's at some kind of angle across the field lines. And then we have heat, so we have some kind of high temperature, so a temperature source here. And then we have a sink over here, for example. And so we have heat flow in a narrow tube down this field line. If you're on this grid like this, then heat fluxes are essentially through grid cells and through cell edges here. And so what happens is that the heat flux down this field line instead gets resolved into heat fluxes through these cells here in the vertical and horizontal directions. And so the heat flux, which should just go along the field lines, ends up essentially spreading sideways. And so you know, with a mixture, here we have like heat fluxes like this. So you end up mixing together the parallel and the perpendicular heat fluxes. And so there's a kind of pollution. So you pollute the cross-field perpendicular transport because there's such a large parallel transport. Now there has been some work to overcome this and improve on this, and one such scheme is by Sibylle Gunther, so quite a few years ago. But you can see this paper if you're interested, which essentially uses a high-order reconstruction method to get high accuracy heat fluxes through a grid like this. So it can be done, but it just needs a bit more care. So if you're interested, see this Journal of Computational Physics paper from 2005, which has a description of a method for how to do that. So in order to overcome some of the problems with these non-aligned grids, so if you want to say treat this very highly anisotropic heat fluxes, or more tricky can be if you want to treat the perpendicular and parallel dynamics differently. So in reduced MHD, for example, the equations for the parallel flow are very different to the perpendicular flow, because the parallel flow is more like a compressible fluid, and the perpendicular direction we have drifts, and so it's almost an incompressible fluid. And so the physics and the equations are very different, perpendicular and parallel to the field. And so one way of treating that accurately is to align the grids with the field. And so by aligning the grids to the magnetic field, we can get several advantages. So we resolve the difference between the parallel and perpendicular transport. We can implement different physics for the parallel and perpendicular dynamics. So for example, drifts in the perpendicular direction. And because in most phenomena, the parallel direction, the wave numbers are very long, because they're typically the size of the machine, whereas k-perp, the perpendicular wave numbers the length scales are kind of Lama radius or that kind of order, and so typically the wavelengths along the field are much less than the perpendicular wavelengths. And so if you align one of the coordinates for the B field, you can have much smaller resolution in the parallel direction, and so you can reduce computation time, you can reduce the number of grid points you need, whereas if you have a non-aligned grid, you essentially need the same grid resolution in all directions. And so if you have a Lama radius scale fluctuations, then this grid needs to be Lama radius scale in all three directions, and that becomes very expensive. Whereas if you use a field line system, your grid needs to be Lama radius scales in two directions rather than three, and then the third direction is the parallel length scale, so it's kind of meters rather than millimeters or less. And so this gives you a very large factor, so typically 1,000 or so reduction in grid spacing you might need. So the first such method to discuss is the flux tube method. An early paper on this is by Beer, Cowley and Hammett. So it's a 1995 paper in Physics of Plasmas, and it describes a system where you have, if this is a flux surface, so this is the toroidal angle, and this is the poloidal angle. So I'm trying to draw, so if I draw this in a tokamak, so I have a torus like this, and here this is the toroidal angle, and then here this is the poloidal angle theta, and I'm going to have radial angle shortly. What we have here is we use essentially slices, so one of the coordinates is in the toroidal angle, so we have a coordinate which is basically a component here in the toroidal angle, like this. And then we take these grid points which are separated in toroidal angle like this, go around here. And it might be simulating just a fraction of a torus, so we might be interested in, say, high N turbulence, for example. We follow these along the field line. So they should all have the same pitch. Like this. So these are going along the field line. So like this. To another set of grid points. So now these are also lined along the toroidal angle. And then here these just keep going. So we go up around the torus. We have a whole set of points. So a whole set of grid points which are spaced around here in polar angle and constant in Z here. So here this is for example phi direction. We have coordinates which are the parallel direction. So this is along B. And so now we might have quite fine resolution in the toroidal angle and quite low resolution in poloidal angle, because this is the parallel direction, as there's very small variation along this direction. And so the kind of coordinate system here is also typically used in Bus for many cases. So the simple definition is just x is just psi, y is the theta angle, which then becomes the parallel coordinates. So now here, if you fix x and you fix z, and you move in y, you follow along the field line, and you move in poloidal angle. And so z is just defined as the toroidal angle minus the shift, which is the shift. So it's the toroidal angle minus the shift that you get when you move along a field line. So it's integral from theta naught to theta. And there's the change in toroidal angle. So if r is the minor radius here. So this is r. And this is b theta to get the pitch of the field lines. The major radius here is r, big R. Okay, and that's integrating theta. So this is a coordinate system. We saw in an earlier lecture, and this is one way of using it is as flux tube. There are a couple of ways of dealing with this. There's a problem here in that this, say, phi, so this theta here, say, goes from 0, and eventually gets to 2 pi. And so this kind of wraps around the torus and ends up coming back. So I'll draw say over here. So it's kind of wrapped around the torus, wrapped around like this. So it's wrapped around, and it's come back at a different location. So it started over here, and it's now ends up over here. And the same way it started over here, it's wrapped around and ends up back at a different toroidal location. So there are a few different ways of dealing with this. One is called the twist shift condition. And in the twist shift condition, essentially you assume that the solution is periodic in this domain. And so you map, typically using Fourier transforms, essentially you assume that this is periodic, and you map this back. So it's periodic here, it's then periodic here, and you map this back into the original domain. So you assume it's periodic in toroidal angle, and you map these set of grid cells back onto the original set of grid cells. And this in general works very well, particularly if you're solving a large fraction of the torus. But if you're solving a small part of the torus, so just a small, say, fraction, say a tenth of a torus or a 20th, to look at high-end modes, then this can introduce additional correlations which are non-physical. The alternative is to wrap multiple times around. So rather than going 0 to 2 pi, you go, say, minus 4 pi to plus 4 pi, and then this is following this tube around and around the torus multiple times. And this is similar to the ballooning transform, where getting transformed from a theta coordinate 0 to 2 pi to a field line distance coordinate, which goes from -infinity to +infinity. And this is the method often used by codes like GS2, for example, where you have multiple 2 pi's in theta to avoid the aliasing or the artificial correlations which this twist shift condition can impose. But many codes like Plus, for example, where you're solving relatively low n modes, you typically use this twist shift condition. Okay, so then one of the big problems with this method is the radial coordinate, and the problem comes about because of magnetic shear. So if we have two different flux tubes, for example, which are close to each other, they will each follow a path like this, but they'll have slightly different pitch. And so if we try and draw this, I'll draw this differently. So if we draw the same graph, we have toroidal angle, poloidal angle. And now if I have three locations, so three poloidal angles. So I have two field lines on each flux surface. I have three poloidal locations, and then I have two different flux surfaces. So choose different flux surface, and we choose this to basically align with this location here at this special poloidal angle. On a different flux surface, the field line pitch will be different. So it might, for example, have a shallower angle. So we have a system, a flux surface which has an angle, and so these field lines at a different pitch, and so any kind of coordinates which will start out aligned will be twisted and deformed. And so if I plot on a different plot what this looks like, so if this is let's say the radial coordinate, and this is now toroidal angle. So I start out with two grid cells here. So these are these points here, and I have two over here. So these are two like this. These are here. So they're overlying each other at the same poloidal angle, same toroidal angle, just different psi. And so we now have a kind of box like this. So computation is quite well behaved. We have a nice square box. If we now go to this here, so at this location up here, I draw the same plot. So now we have again 2 points here which come from here. And now the red points have moved further in toroidal angle, and so rather than being over here, they're now over here somewhere. So we end up with a sheared box like this. And then if we go to the other side, of course, the shearing is in the opposite direction. And the shear can become very large if the radial coordinate is not fine enough, particularly if you have things like X points or just near the edge of the plasma, where this shift can become very big. And this leads to a problem when you try and match this side. So when you try and do the twist shift condition, say, and match this side onto that side, you have to match a whole bunch of grid cells which are sheared this way onto grid cells which are sheared that way. And this tends to mix together the radial coordinates, radial derivatives, and the toroidal derivatives, and this leads to numerical problems. So you mix the derivatives in toroidal angle and derivatives in psi together, because you're taking derivatives along these shared coordinates here. And there's a particular special location in the plasma because you now essentially treat the box as continuous like this, and then at the ends you match onto the other side, and so suddenly the shearing switches from this to that, and so there's a special location where that matching location occurs. And in this particular method, if you use this coordinate system, if you look up here, there's a problem when b theta becomes small. So if you have an x point, for example, this method has a singularity because the parallel coordinate and the toroidal coordinate become the same, and so this has a singularity. So one partial solution to this is the shifted metric method, and for this you can see a Bruce Scott paper, and the idea is just essentially to reset the coordinate system at every poloidal location. So rather than having a deformation of the grid cells and then matching at the ends, we just match multiple times onto each grid cell. And so you can plot this instead as something like this. So we have again toroidal angle, poloidal angle, and now each set of points is just always at the same set of angles like this. So we have a set of points in theta. The field lines are still doing something like this, and then at this point here we match. So we have these grid cells here, we have these grid cells here, and then match the two onto each other using periodicity. So essentially it's doing twist shift on every poloidal plane, every point in poloidal angle. So this reduces the distortion of the grids. You no longer have such large shear, and it means there's no longer a special location, a special poloidal location where the twist shift occurs. And this generally reduces many of the numerical issues associated with this kind of sharing problems. It still has the same singularity problem as the simple flux tube method, but it is a definite improvement for many non-linear problems in particular. So one of the problems with both the shifted metric method and the original flux tube method is that close to the edge of the plasma, where the poloidal field can become small, a cube becomes quite large, these planes here, the field line pitch can become very close to toroidal angle, and this means a loss of accuracy because the coordinate system becomes very non-orthogonal. And one way of improving that is to use a simple toroidal coordinate system, and this essentially just flips this sideways, so it reverses this kind of theta to phi directions. And so instead of having a set of planes at fixed poloidal angle, we now have planes at fixed toroidal angle. So we have these kind of planes like this, which now must go 0 to 2 pi. So this is going 0 to 2 pi here in theta, and this is toroidal angle. So now I have planes in fixed toroidal locations, and now the field lines, which are doing like this. So we have a set of grid points near the edge of the plasma. This doesn't necessarily have a singularity, although most coordinate systems that you write down for this would. But what it does mean is that these angles are much closer to 90 degrees, and so there's much better separation. So it's usually more accurate. There is a downside though, is that you now have to solve the whole 2 pi in theta, so you have to have a high accuracy grid in all of 2 pi of theta, whereas for example here we have a relatively coarse grid in theta, and so it's just resolving the equilibrium variation, whereas here this needs to resolve the turbulence, like small scale structures. So this needs to be very high accuracy in theta, whereas this could be quite low accuracy or low resolution. And finally, one of the problems with this is that you If you're solving in full geometry, this theta, the metric tensor, is changing in theta. And so that means it's very difficult to use things like Fourier transforms in theta, whereas at least in a tokamak, the metric tensor, for example, is constant in phi, in the toroidal angle. And so to solve on these coordinates, you can often use Fourier transforms or other high accuracy methods, whereas those are generally not possible in this plane here. Okay, so finally there's one variation, so essentially taking this method here and generalizing it to more complicated cases. So here what this is doing is saying we have coordinates which are at fixed phi, and we have a simple structured grid in each flux surface. What the FCI method does is generalize this to 2D or to fully 3D fields, and so it's applicable to things like stellarators as well as tokamaks. And what this also does is it gets rid of any kind of requirement to have nested flux surfaces, whereas this scheme and all previous schemes looked at, they take a 2D flux surface at a time, and so each flux surface is treated independently. What this coordinate system does is it drops any requirements, so it says we don't even need to have flux surfaces. You can just have stochastic fields or complicated flux surfaces where we don't really want to follow the exact structure. And the basic idea is really quite simple. It says you choose a set of grid cells, and these are high resolution. So these would be kind of rho I kind of length scales. These are long radius kind of scales for resolving turbulence. And then now we want to calculate derivatives along the field line. So the idea is that you have multiple of these planes. So this might be, say, in toroidal angle. So we're taking essentially planes like this at fixed toroidal angles, although that doesn't necessarily need to be that restrictive. So say again have a set of grid cells. I'm drawing approximately the same amount, but it doesn't actually need to be the same on this as on that. And we have one over here, for example. So we have a set of 3 grid planes. We're solving a set of equations on these planes, and this would be like for example the perpendicular plane. So you might have E cross P drifts in this plane, and then we want a parallel derivative. So you take this grid cell here, we follow along a magnetic field onto a neighbouring plane, and we find out where it intersects. And so these crosses mark the intersection. So this is like the B field here. And so we find out where they intersect, and then we do an interpolation. So we take nearby grid cells here, and we interpolate. And so if you want a parallel derivative, you trace along field lines. You might only need to do the tracing once, say at the beginning of the simulation, if the magnetic field is static. You find out where they intersect, you calculate the values at the ends of these field lines, and then you have 3 points along the field line, and you can calculate a derivative. So it's conceptually quite simple in a way that you simply choose a grid that you want, then you trace along field lines and you interpolate using typically a high order interpolation method. Otherwise this can be a limiting factor in your accuracy. The advantage is that this still retains a lot of the advantages of field line methods, because you still have a low resolution in the toroidal angle. You still only need a high resolution in the 2D plane, and this gives you a lot of flexibility. The downside is, for example, it can be quite expensive to do these interpolations, because you have 2D interpolations, whereas for these schemes you sometimes need an interpolation to do this mapping, but it's typically one-dimensional. Each of these is a separate one-dimensional interpolation. So these things tend to be quite fast. So FCI does come with additional complexity and expense, but it means that you can solve very complicated fields. So you can have, so draw a different color here. So you have a separatrix, for example, or a complicated X-point structure, so where poloidal field goes to 0 at this point here, for example. But the FCI method doesn't care. It just still works exactly the same way. So you might have an X-point structure, for example, or you could have stochastic fields or anything else. All that matters is you can follow a field line, and if you have a strong guide field, then that's essentially guaranteed. So you have a strong guide field in a tokamak or most toroidal devices. Reverse field pinches might have a problem, but things like tokamak and stellarators, this works very well. An example paper is by Hariri and Ottaviani, and many others since then. So there's now a code called Grillix which uses this scheme. I'll put a few references here. So there's this Hariri and Maurizio Ottaviani paper from 2013. There are many other papers. So Grillix is Andreas Stegmaier has written a lot of papers using and developing that code. Fenicio was the code used by Hariri, and so it's developed at CEA. Butterplus, of course, can do all these methods, including this FCI scheme. And so there are papers you can have a look on online for that.